Good morning, students. So today's class we are going to study about the characteristics of FIR filter with the linear phase. So FIR, as we know that the FIR filter has linear phase characteristics. That means the angle is linear. So to prove that we have a derivation for the FIR filter. Now let us consider h of n, which is a finite duration sequence, which is an impulse response function. We are going to take the Fourier transform for the h of n. So when you apply the Fourier transform for h of n, we will be getting the equation as h of e power j omega equal to summation of n equal to 0 to n minus 1 h of n e power minus j omega n. So here when we consider the signal as a periodic with period 2 pi, in that case, the h of e power j omega becomes h of e power j omega plus 2 pi m, where m is an integer which varies between 0 plus or minus 1 plus or minus 2 etc. Now, when you take the Fourier transform of h of n, we will get the frequency response. This h of e power j omega, we call it as a frequency response. So, for the frequency response, we have some magnitude function as well as phase. The magnitude function is expressed as plus or minus modulus of h of e power j omega into the angle is expressed as e power j angle of h of e power j omega. So the amplitude function or magnitude function, we call it as a of omega, and angle is e power j theta omega. So a of omega is an amplitude function which is equivalent to plus or minus modulus of h of e power j omega, and theta of omega we call it as a phase function. So for any frequency response of the signal, the magnitude is symmetric and the phase is antisymmetric. So this is proved by modulus of h of e power j omega equal to modulus of h of minus e power j omega. So this shows the magnitude is symmetric, and modulus of theta of omega equal to minus modulus of theta of minus omega. So here we have a minus symbol before that modulus terms. So hence the phase is antisymmetric. So now we are considering the h of e power j omega. The phase of the h of e power j omega is a linear function of omega. So that's why the theta of omega is directly proportional to omega. So here when we write it as theta of omega, it is equal. That means we are introducing a term called alpha. This alpha, it is nothing but it is a constant phase delay. So now the theta of omega equal to minus alpha omega, where omega varies between minus pi to pi. Now again we are going to take a frequency response equation, so which is given by h of e power j omega equal to summation n equal to 0 to n minus 1 h of n into e power minus j omega n. In this frequency response we have expressed in terms of magnitude function as well as phase. So the magnitude function is nothing but plus or minus modulus of h of e power j omega, and the angle it is nothing but e power minus j theta of omega. Already we have assumed theta of omega is minus alpha omega. So that's why we have substituted the minus alpha omega in this particular equation. So now we got the frequency response of the filter, which is having the magnitude function as well as phase. Now we are going to equate this particular expression with summation n equal to 0 to n minus 1 h of n e power minus j omega n. So then we are going to expand this e power term both in the left hand side as well as in the right hand side. Just the e power term alone we are going to expand. So first expression summation will be remain as such. That means summation n equal to 0 to n minus 1 h of n. Now when you expand this e power minus j omega n, we can expand it as cos omega n minus j sin omega n. This is equivalent to, again the modulus term will be remain as such as plus or minus modulus of h of e power j omega, and e power minus j alpha omega we are expanding it as cos alpha omega minus j sin alpha omega. So just we are expanding this. Next after that we are just segregating the cos term separately and the sine term separately in that equation. Now in the left hand side we are segregating the cos term and then equating with the equation in the right hand side. And then we are segregating the sine term and equating with the sine term in the right hand side. So if you see plus or minus modulus of h of e power j omega into cos alpha omega equal to summation n equal to 0 to n minus 1 h of n cos omega n. Similarly, we have segregated the sine function and equated here. After that, we are going to let us consider the above equation equation 1 and below equation as equation number 2. So we are going to divide the equation number 2 with equation number 1. So if you divide this, so we will be getting sine alpha omega by cos alpha omega equal to summation n equal to 0 to n minus 1 h of n sine omega n divided by summation n equal to 0 to n minus 1 h of n cos omega n. So we will be getting this particular expression. So after that we need to cross multiply these equations. So when you cross multiply this equation, sine alpha omega it is multiplied with summation n equal to 0 to n minus 1 h of n cos omega n, and this cos alpha omega it is multiplied with summation n equal to 0 to n minus 1 h of n sin omega n. Now in this equation, we are bringing the sine alpha omega inside that summation and cos alpha omega also inside that summation. Then we are subtracting this and equating with 0. Now when we arrange the equation as we are taking summation n equal to 0 to n minus 1 h of n as common, then you will be getting the equation as sine alpha omega cos omega n minus cos alpha omega sin omega n. Now this equation it is in the form of sine of a minus b. So according to trigonometric formula, sine of a minus b equal to sine a cos b minus cos a sin b. So now this equation becomes summation n equal to 0 to n minus 1 h of n sine of alpha minus n of omega equal to 0. So here a equal to alpha, b equal to n. So we have substituted, we are getting this particular equation. So after that, the solution for this particular equation is alpha is n minus 1 by 2 and h of n is h of capital N minus 1 minus n. For n, small n varies between 0 to n minus 1. So this is the solution we will be getting. So now to prove that, let us take this equation h of n sine of alpha minus 1 alpha minus n into omega. So we have taken to prove it. So h of n we have substituted here. Sine alpha it is n minus 1 by 2 we have substituted here minus n of omega. Now when you cross multiply this 2n and take an LCM of it, so it will be n minus 1 minus 2n divided by 2. After that this minus 2n we can write it as minus n and again if you see n minus 1 minus n it is equal to n. So it is n minus n divided by 2 which is equivalent to 0. So h of n into sine 0 then it is 0. So hence we have proved that h of n sine of alpha minus n into omega it is equivalent to 0. So then alpha which is nothing but n minus 1 by 2 it is an impulse response as some special kind of symmetry.